At the core of this design is a VEX differential, a motor sharing technique which seamlessly shares 4 motors between the drive and tilter. A substantial number of teams already utilize differentials, but this design has been developed over a number of years to minimize frictional losses. Today, we will analyze basic differentials and how the specific one functions. In the automotive industry, differentials have long been utilized, but in VEX, the concept is applied in a very different way. 2 inputs control 2 outputs based on the difference in their speeds. So you can run the first output with complete power from both inputs, then swiftly apply the full power to the other output, or any combination of both. There are 2 basic designs for achieving this, and they are called VEX differentials. Also note that these can be modified while still functioning the same way, and that other even more complex differentials exist, though they will not be covered in this video. Out of the 2 basic differential designs, we are using this one because the motors are connected directly to the drive, as opposed to the other design where the power is transferred through a much higher friction transmission. However, the major problem is that when the drive is being powered, these gears resist motion, which puts extra friction on the axles, causing frictional losses. Our solution is a custom bearing block. It consists of a 393 motor internal gear with a hole drilled through to allow room for a free spinning axle. A slightly drilled gear allows it to sit on this piece, taking any force off the axle. In the design, the motors sit in so-called cores with 2 motors per core. This is because there are 2 differentials, with their second outputs connected, both powering the tilter. They connect to the tilter with a forebar, which locks the tilter in the up or down position, as well as increasing the torque. We however needed to add a higher gear ratio in between the differential and tilter, which meant the cores, which contain the motors, would need to make multiple revolutions. It was vital that the wires don't get caught in the gearing, while still allowing the cores to make around 3 revolutions. The solution was rubber bands pulling the wires. The rubber bands had to be long enough and connected to the tilter, which moved with the rotation of the cores, getting farther when the wires unraveled and closer when the wires rolled back up. With that, the differential was at its current state. Thanks for watching.